Hello everyone, welcome to the fifth lecture of this Microsensors and Nanosensors course. This will be essentially the final lecture in this module of Introduction and Classification of Sensors. In the previous class, we were discussing chemical vapor deposition and we have learned the basic working of a CVD system. We have also seen various kind of CVD setups. Okay, mostly the CVD setups are based on different pressure that is there inside its main chamber. Okay, we have atmospheric pressure CVD systems and low pressure CVD systems. Okay, both can be hot wall tube and cold wall tube based CVD system. Okay, cold wall tube are mostly continuous motion and batch type of CVDs. Okay, and in low pressure we can also design some PECVDs. Okay, PECVD can also be a hot wall batch and cold wall single wafer. Apart from this, based on precursor also, in the previous class we have seen some CVDs like MOCVD, metal organic CVD systems, where the precursor itself is metal organic in nature. Okay, so this was all about CVD that we have learnt in the previous class. So once I know this deposition, I will discuss the physical vapor deposition also in some time. But before that, let's take a quick pause and let's know the oxidation, because oxidation is very crucial in this microsensors and nanosensors fabrication, and it can be grown as well as deposited. Since we have already some background on chemical vapor deposition, it will be very easy to understand oxidation, and after this we will learn physical vapor deposition. Okay, so one of the crucial oxide in the sensor fabrication is silicon oxide itself. Okay, apart from this, as I have mentioned, that tungsten oxide, molybdenum oxide, they are, and some other oxides, they are essentially the main element or main receptors of the microsensors, particularly for chemical sensors. But silicon oxide remain the major oxide that is used in the microsensor. So among various semiconductors, silicon can oxidize its surface very easily, which make it very unique, and that's why we know that the complete microelectronics is revolving around this particular semiconductor. Okay, formation of SiO2 layer can be done in both ways, like you can deposit it as well as it can be grown from wafer itself. Okay, for deposition we have mostly plasma enhanced CVD and some physical vapor deposition that we are going to discuss in this lecture. And apart from this, there are some other chemical methods like sol gel method. Okay, and for growing silicon thermally, okay, what we do is we actually consume the wafer itself. Okay, we take some amount of silicon from it, and by some selective oxidation we can grow whatever required amount of oxide we require. Okay, and please note that this is the best quality of oxide that we can get, and mostly this is used across the industry. Okay, so different type of silicon oxide is required depending on what kind of device you are working on. Okay, or even in a single device you may have requirement of different oxides. You may require a filled oxide which has a typical thickness of around 400 nanometer to around 1.4 micron. Apart from that, you need masking oxide, pad oxide, gate oxide, and apart from this you have already some native oxide. Okay, the typical thickness of this native oxide is around 0.5 to 2 nanometer, while in gate oxide usually we have 1 to 10 nanometer. Usually even if your device is going to, the size of device is increasing, with that also gate oxide doesn't change much. Okay, then pad oxide is a requirement of for the sensors fabrication as well as some microelectronic device fabrication, and typically its thickness is around 10 to 40 nanometer, and for masking and all you need silicon oxide itself, so its thickness is around 60 nanometer to 400 nanometer or so. Okay, so you not only need silicon oxide, but you also need it in various thicknesses. Okay, so you should ensure that whatever method you are going to adopt for the fabrication of or for the growth of this silicon oxide, you should have control over its thickness. Okay, so talking about deposited oxide, usually where silicon is not directly exposed, there you have to deposit something. Okay, if silicon itself is exposed, you can use the thermal oxidation process, but where it is not exposed, say there is some other layer, but say it's a metal layer. For example, on silicon you have silicon oxide, thermally grown silicon oxide, on top you have some metal, and on top of that you need silicon oxide. There you cannot grow because there is no silicon at all, right? So for those cases you need to deposit. Okay, so as I have mentioned that we can use some CVD systems like PCVD, LPCVD, that kind of setups to process this particular request. You have not that good control as you have in thermal oxidation for this particular growth. Okay, and usually this chemical vapor deposited SiO2 is not preferred when the thickness required is very less. Okay, for those cases mostly you rely upon thermal oxidation. Okay, so let us learn about thermal oxidation, because this is the most sought technology in microelectronics. Okay, so mostly the oxide, the silicon oxide that you obtain by thermal oxidation are amorphous in nature. Okay, they are the oxide is very stable, the process is very reproducible. Okay, so oxidation require a very high temperature, around 900 to 1200 degrees Celsius for the growth of silicon oxide. Since the underlying silicon is consumed, okay, the SiO2 interface moves deeper into the wafer with the oxidation. Okay, mostly this oxidation is of two types. You have a dry oxidation and a wet oxidation. Okay, let's learn about dry oxidation and wet oxidation in very brief. Okay, wherever you require oxide thickness of around 0.05 micron to 0.5 micron, typically means less thickness is required, you have to use dry oxidation. Okay, and these oxides grown by dry oxidation are can act as excellent insulator. And mostly since you know that gate oxide thickness is very less in field effect transistors, okay, dry oxidation is preferable. So from this reaction you can see that the precursor required is only oxygen. Okay, since there is no water molecule involved here in the process of deposition, okay, I am calling this a dry oxidation. This is a typical dry oxidation process. You have a tubular kind of furnace in which your wafers are vertically mounted. Okay, and you have a carrier gas in the form of nitrogen, and you have this oxygen as a reacting species. Okay, and you introduce with some control, with some mass flow controller inside this tube, and it is heated radially at around little bit higher than 900 degrees Celsius, and you obtain a very thin oxide on this wafer. So from this, the position of this wafers or from the loading of this wafer, you can clearly see that you can oxidize multiple wafers in one go. Okay, so you don't have to push every wafer individually. You can oxidize at a time a number of wafers depending on the loading capacity of the tubular furnace used in the process. Okay, for little thicker oxide you use mostly wet oxidation. Okay, so wherever you need much thicker oxide, you should choose wet oxidation, although the quality of oxide that is grown in by dry oxidation is pretty good as compared to the wet oxidized wafers, but then also it requires a lot of efforts to grow thick oxides using dry oxidation. So we should always avoid dry oxidation for thicker oxides. Okay, and typically thickness of the order of 2.5 micron are grown by wet oxidation process. Okay, usually it is not preferable for gate oxide growth. However, it is very good process for field oxide growth and for masking purposes. Okay, as you can see, the precursor here is H2O vapors. Okay, so you have water carrying bowl kind of thing, which is connected through some pressure control gauge, and again you have oxygen and you have a carrier gas through which it is inserted into this chamber at elevated temperature of around 900 degrees Celsius to 1200 degrees Celsius. Okay, and it forms a very good SiO2 layer, better than the chemical vapor deposited oxides. Okay, so this dry oxidation and wet oxidation are always preferable methods, except those places where you do not have exposed silicon. Okay, you use a chemical vapor deposited method. Okay, now I have given you a brief idea of oxidation, and you already know the chemical vapor deposition. So let's come back to our original topic of deposition. Okay, which is in the series we have learned the chemical vapor deposition. Okay, the second part is the physical vapor deposition. We have just covered oxidation because that is very crucial for the microsensors fabrication, and it also involves some deposition. So I have covered it in between the deposition topics. Okay. The physical vapor deposition is a preferable method for thin film fabrication in microsensors, and that's why it is very necessary to know in brief about this PVD methods. Okay, PVD methods are mostly of two type. Of course, there are some other type of PVDs, but mostly this is of two type. One is evaporative and second is sputtering. Okay, evaporative means you have a metal source and you just heat it above some temperature and by some mean. Okay, and the atoms are dislodged in the process of thermal agitation, and it get deposited and it finds some cold place inside some vacuum chamber and it get deposited. Okay, and by this you have a very good thin film deposited. Okay, in the sputtering process, what we do is we try to bombard some particle or some ions on a target element. Okay, target can be some metal, some insulator, or sometime some semiconductor. Okay, we bombard it with some atoms or some ions or some particles. Okay, with some small projectiles. Okay, and in the process this projectiles dislodge some atoms from the target, and again by cooling method it deposited in the solid form and it form a thin film. Okay, so evaporation method can be of various type. We'll try to cover some of them. It can be simple thermal evaporation. Okay, it can be based on electron gun. We call it e-beam evaporation. Okay, similarly based on heating you have inductive evaporation, resistive evaporation, and all. Okay, similarly sputtering can be of various type. A simple DC sputtering, sometimes also known as diode sputtering. Okay, and apart from that you have a magnetron sputtering, ion beam sputtering. Okay, and so on. Okay, RF sputtering for high frequency sputtering system. We'll see some of them in very brief. Let's see the thermal deposition first. Okay, usually this thermal deposition system works under a vacuum. All this deposition is done under certain vacuum. Okay, so this typically the vacuum chamber is around 10 power minus 6 torr or so. Okay, and you go ahead in sputtering and all, you require more and more vacuum, and in case of molecular beam epitaxy and so you need very high vacuum to be achieved for deposition. Okay, but in the return you get very good deposited film. Okay, so in this thermal deposition system what we do is source is heated to the point where it will be evaporated. Okay, a source of the metal to be evaporated is placed below the substrate. So usually this substrate is mounted on a curved surface. Okay, so it is usually stick with something, and if you want to do patterning at the same time, you may need some shadow mask or something which will have some physical pattern of that particular thing. Okay, so you put your substrate like this hanging. Okay, and your metal source is put in the small bucket over here, which is we call a crucible. Okay, so you heat it after achieving the vacuum. Okay, by passing, if it is a resistive heating, you pass very high current through it and it is heated. Okay, and by achieving this Joule heating, you achieve a certain degree of temperature, and this is evaporated. Okay, and in the process of evaporation, it go and find some cold surface where it get deposited. Of course, it also find the side walls of this chamber, where also you will find some of the deposited metal. Say for example, if I am depositing aluminum, so you will find some of the aluminum on the side walls. Sometimes this chamber may have some, something like this. This is some transparent area through which you can see that this deposition is going on or not. Okay, so sometime you will find that this transparent area also becomes opaque when this deposition is happening. Okay, because you do not have projectile control in this particular process. Okay, this metal particle can go and deposit on the side wall also. Okay, so in this process there is difficulty to control the rate of evaporation. Okay, then you have another kind of deposition, which is e-beam evaporation. In this process, again, it is heating process only, but you have better control over emission current. Okay, so source material is placed in a crucible which is heated by a very large current by the filament. Okay, and the emission current arises from thermionic emission by some electron is accelerated, and then this electron beam is twisted by the magnetic field towards the source material. Okay, and when it reaches source material, again it heats it, and the metal element get ejected from its surface, and it go and it get deposited on the wafer. In some of the advanced system, some rotation is done to have a uniform film, and sometime you have a QCM deposition monitor, which can give you an idea of deposited thickness of the film. Similar QCM deposition monitor is also possible in thermal evaporation system that we have just discussed. Okay, so this is a basic thermal evaporation system. You can achieve a certain level of uniformity in this e-beam evaporation system over the thermal evaporation system that you have just seen. Okay, however, the most advanced deposition systems are based on sputtering. Okay, so sputtering is used where your substrate cannot be, or your target material, that the metal should not see very high temperature. It should not be heated to that particular temperature, and mostly this process is CMOS compatible. Okay, so another method that is very suitable for thin film deposition in the fabrication of microsensors and nanosensors are sputtering. Here, both the target which you want to deposit on some substrate, so the target and substrate both are placed in a vacuum chamber. So the target acts as a cathode and substrate acts as a anode. Okay, plasma is generated by ionized sputtering gas, which is then bombarded on the target and sputter of the material to be deposited, and this material get deposited atom by atom on the substrate, which is again placed at the anode. Okay, so if I tell you this complete process in brief, the source is bombarded, as you can see. Source is bombarded with high speed particles. Okay, so source, this green particles are the source, which is these atoms are bombarding over the source. Okay, and these particles, when hit this source, some of the atoms from this source get dislodged. Okay, because there is a momentum transfer from this high energy particle to this source. Okay, and due to this momentum transfer from particle to the surface atom, this source atoms start escaping from the surface. Okay, and the ejected atom travel to the substrate and deposit over here as a thin film. Alright. So the process is as simple as this. Okay. The sputter yield will depend on the kinetic energy of these particles, okay, mass of the ions or mass of these particles, the binding energy of the surface atoms, okay. Binding energy of these surface atoms, if it is very high, they don't want to leave the surface of source, okay. So it will also depend on the binding energy of the source atom and their mass, okay. There are various type of sputtering. We will not be able to cover all of them, but I will just give you an overview of all these systems. We have DC sputtering, RF sputtering, magnetron sputtering and reactive sputtering. Mostly these 4 type of sputtering are used, particularly magnetron sputtering is very popular in microsensors fabrication. Okay, so DC sputtering is very simple. You provide some DC bias to this target substrate setup. Okay, so you provide some negative potential to the target, and mostly this substrate is grounded, so it is at particularly positive potential as compared to the target. Okay, and typically you can range this potential like 500 volt to 1000 volt. Okay, however, the sputtering is possible in this case only for the conductor, okay, and not for insulators and semiconductors, and therefore we have RF sputtering where the applied voltage oscillates at RF, okay, particularly at 13.5 megahertz, okay. And the deposition of insulator and semiconductor is also possible by this process, okay. Then you have magnetron sputtering where the magnetic field behind this target controls the charge ion particles behavior, okay. So you have a magnetron in place, okay. And the final is the reactive sputtering where which is a combination of physical and chemical deposition. So apart from the physical ions that you introduce for bombarding the source or the target, you also introduce some gas which can chemically react, okay. So this is all about the deposition, okay. So it's a very huge topic. Mostly you will find it in the fabrication course. However, for this course, this introduction is more than enough, and we'll discuss any of the method if it require in our course, okay. Then complementary to the deposition, we have a process which is known as etching, okay. So etching is basically a removal process, and as I have told, it is just complementary to deposition process, okay. So it is a controlled removal of material from a substrate via chemical or physical method, okay. It can be considered as a permanent transferring of mask pattern from photoresist to wafer surface. Till now in the lithography we have seen that the mask pattern, the pattern in the mask has been transferred in the wafer, but on the top of this wafer you have photoresist coated. And we have also mentioned that photoresist is a temporary thing, we have to remove it, okay. So this process is not permanent till we do the etching. If you remember, I have shown you one figure in the previous lecture where we have a patterned photoresist. However, this pattern has to be transferred on the thin film, okay, something like this. You have a deposition of the desired film. Already you know the different deposition method. You can use any chemical vapor deposition method or some physical vapor deposition method. On top of that, you have coated the photoresist and you have done the patterning of photoresist, okay. So this orange thing is the patterned photoresist, okay. Now what I have to do is, this is a temporary transfer of the mask, okay. This pattern was in the mask and we have temporarily transferred it into the photoresist. Now I have to etch down this particular area of the film, okay, and this is called etching, that we are discussing now, okay. and then after this etching process you can easily remove the photoresist and your pattern is transferred permanently into your thin film. Okay, and that's all about the lithography process. Okay, generally there are two type of etching possible. One is wet etching and another is dry etching. Okay, so in wet etching what we do, we immerse the wafer in a tank of chemicals. Okay, it can be a single chemical or a mixture of etchants. Okay, have a look on this. You have a silicon wafer, you had some oxide over here, okay, which of course you have to etch. Okay, and you have reactants in this solution. It can be again a single etchant or a mixture of etchants. Okay, and then it reacts with this oxide layer and it produces some byproduct. Okay, so the wet etching process is very simple. What you do is you immerse your wafer in a tank of etchant, mixture of the chemicals. Okay, there is a chemical reaction between the wafer surface and the etchant that helps in the material removal. Either a photoresist layer or a hard mask like this oxide or nitride is used to protect the other part of the wafer. Okay, the time of etching depends on the amount and type of material that need to be removed. Okay, we'll see this with one example. Okay, let's take example of KOH, which is a potassium hydroxide, which is a common etchant to remove silicon. Okay, usually 30% KOH solution is used, which has a etch rate of around 100 micrometer per hour when it is heated at 90 degrees Celsius. Okay, so if you use this particular solution to etch down some structure at 4-inch wafer, okay, and if the thickness of the wafer is 500 micrometer, okay, it will etch down the complete wafer in 5 hours. Okay, so you have to be careful that what thickness of wafer you are using. Okay, what is the structure that you want to use and what is the mask that you are using to protect particular area. Okay, and also please remember that these etchants will have different etching rate across different orientation. Recall the orientation that we have studied in our second and third lectures. We have seen N100 wafer, we have seen N111 wafer, we have seen P100 wafer, P111 and P110 and other kind of wafers with different doping profile and different orientations. Okay, so these etchants will have different etch rate in different directions. Okay, so different orientations wafer may have say the etch rate of KOH along one direction will have different value as compared to its etch rate along 110 or along 100. Okay, so while choosing different type of etchant you should be very selective. Most common wet etchants are isotropic in nature. Okay, so isotropic means you have same undercut. The isotropic means you have cut in all the directions equally. Okay, so if in this structure if B and D are equal, I can say that it is perfectly isotropic. Means etching stops before reaching the bottom of the film. Okay, usually over etching is used in non-uniform film. We'll see that in a while. Okay, and for anisotropic etching, sometime over etch is needed to remove residual film. We'll see some of the challenges in etching, and in it we will cover the over etch and under etch. Okay, but before that let's see what is incomplete etch. Okay, this is a typical example of incomplete etch. Okay, here the time is not sufficient for complete removal of the oxide or any other thin film that I want to etch out. Okay, it is mostly due to concentration or insufficient temperature. Say if the concentration of the say take an example of the KOH that we have just seen. Say I need 30% KOH to whose etch rate I know. Okay, but in place of 30%, say if I have 25% KOH. Okay, and as I have also mentioned that etch rate was mentioned at particular temperature, like in KOH case it was mentioned at 90 degrees Celsius. Say if the concentration is 30%, but this temperature is not 90 degrees Celsius, say this is 70 degrees Celsius or say 80 degrees Celsius, okay, you may have incomplete etch in the process. Okay, then variation in concentration is also one of the challenge where you may end up getting a rough surface. Okay, then last time we were seeing the over etch and undercut. Let's see what it is. Okay, if etch time is larger than the required one for isotropic etch, material under photoresist get removed. Of course you do not want it, but this can happen. Okay, because you have given etch time much larger as compared to the required one. Okay, so it is just opposite to incomplete etch. In incomplete etch you were not able to etch down the film completely. However, in this case, although you are using a oxide to protect some film, but since you have dipped it in a etchant for longer time, you know, etchant wet etch can etch down the film under the mask also. Okay, so this process results in undesirable sloped side walls, and the vertical thing that you wanted like this is not achieved. Okay, so ideal etchant should be selective and anisotropic in nature. Okay, extreme case in over etch can lead to sometime lift off of the resist layer. Okay, it is undesirable as it exposes the unwanted area during the etching process. Okay, so usually you do not want the lift of the resist because you have kept it for the other processes. Okay, third thing is etch selectivity. So etching process should be selective to the material that is being removed, and apart from the material you should also know the orientation of the material. Okay, because the etchant's etch rate will also depend on that particular thing. Okay, then second type of etching is dry etching. Okay, it refers the removal of material in the absence of any solvent. Okay, it overcomes some of the limitation of wet etching because solvents are not in place. You have some gases or some other species through which you do etching. As the name suggests, it is a dry process. You do not have any wet solvent available here. The etchant gases are the primary medium for the removal of the material. So usually the etching is done by using some gas molecule. Okay, there are mainly three type of dry etching: plasma etching, ion beam etching, and reactive ion etching. This is a typical plasma etch process. Okay, so it is a chemical dry etching process. The gas is ionized by plasma, which is generated by the RF. Okay, by attacking the oxide layer, the ionized gases remove the layer. Mostly CF4 is used for Si2 silicon oxide etching by plasma etching process. Okay. However, mostly nowadays this plasma etching is not used. Okay, you have other advanced etching processes available with you. Okay, so ion beam etching is one of the method. So as again it is a dry process, so it is a physical dry etching process where argon ion beam of about 1 to 3 kilo electron volts are radiated on the surface and strike out the material that you want to etch. Okay, and this process is absolutely anisotropic process. However, the selectivity is low. Okay, so it cannot differentiate silicon with SiO2 or any other material. Okay, so the process is not selective to particular method. Okay, and that's why we require some advanced etching processes. Okay, in the process you have reactive ion etching, which is very popular method in the fabrication of microsensors and nanosensors. It combines the plasma and ion beam etching to achieve both selectivity and directionality. Okay, all the etching characteristic can be controlled very precisely over here. Okay, here the used gases are mostly oxygen and CF4. Okay, usually the reactive ion etching process are of two type: capacitive RIE and inductive RIE. Capacitive RIE has mostly low density of plasma, while inductive reactive ion etching have high density of plasma. Okay, so derived from this RIE, we have a DRIE process. Okay, it is special subclass of RIE, and it is used to etch deep cavities with higher aspect ratio. Okay, please note that aspect ratio is nothing but cavities depth is to cavities width. Okay, the ratio of its depth and width. Okay, most of the this DRIE process uses Bosch process. Okay, Bosch process is nothing but a cyclic process of deep etching, where you use a passivating layer of say for silicon you use C4F8. Okay, for passivating, and for etching you use SF6. Okay, so it enables very deep etching of silicon using fluoropolymer as passivating layer, and it uses a cyclic process. Okay, so in very brief, what is etching in fabrication of these microsensors and nanosensors? Okay, so once we understand the etching, we should also know the doping of a silicon or some other material, because it is used not only for the wafer purpose, but doping is also crucial for the receptors. Okay, so usually doping in microsensors and nanosensors are achieved by two processes. One is thermal diffusion, and the second process is ion implantation. Okay, the maximum concentration of the dopants in thermal diffusion process is at the surface, as you can see in this figure. So this shows that the maximum concentration of dopants are lying near the surface. Okay, however, the dopants start diffusing into the wafer with time and with temperature. Okay, and this is used for forming the source and drain regions of FET based sensors. Okay, in this process there is no damage to the crystal, and high quality junctions can be obtained with minimal leakage current. Okay, and at the same time deep junctions can be formed. Okay, there are different type of diffusion processes, like you can have interstitial diffusion, substitutional diffusion, combination of interstitial and substitutional, which is called interstitial substitutional diffusion, interchange diffusion, grain boundary diffusion, and combination effect of all these five diffusion methods. Okay, so depending on where these dopants are going, okay, in a crystal, I can have different diffusion process. Okay, then second kind of doping is ion implantation. Okay, and this ion implantation tool is really a costly tool, but then also it has evolved as an alternative technology to the diffusion type of doping, because thermal diffusion process is an isotropic process. Okay, so lateral diffusion you cannot avoid. Okay, diffusion coefficients in different crystallographic direction can be different, which is one of the limitation of the thermal diffusion. Okay, doping control is also difficult to achieve due to presence of concentration gradient across the surface and the bulk. Okay, and there is a thermal budget associated with the doping. Okay, so ion implantation has emerged as one of the advanced technique in doping, and you can have a very precise control of doping. As you can see in this figure, that maximum concentration of the dopants are located just below the surface, and the diffusion across this area are minimal. Okay, so in this process the dopants are embedded below the surface itself. Okay, and this is done by some electric field which can accelerate the charged ion. So very high energy dopant ions are smashed into the crystal lattice, which is introduced into the crystal which you want to dope. Okay, but this process can damage the wafer, or if you want to dope a receptor, so this process can damage the receptor's film quality. Okay, then another process is metallization in the fabrication. Okay, so you require a lot of metal patterns for the sensor, be it fabricated on a silicon wafer or be it fabricated on flexible substrate or any kind of substrate. Okay, you require interconnects for establishing connections with the outer ambient. Okay, so metallization require some kind of caution, as you have seen in required in doping. Okay, ensuring that no metal interacts with any part of, say, if it is optical sensor, then it doesn't interact with any optical mode of, or if it is a chemical sensor, it do not interact with any other portion or any other part of particular chip. Okay, so metallization can be done by various means. You can have a thermal deposition method. Okay, the sputtering method that you have seen can be a very good metallization technique. Okay, CVD is one of the very quick method for depositing some of the important metals that are used in interconnects. Okay, then electroplating is also used for some time for copper, particularly the for the copper deposition. Okay, so these are some of the methods used for metallization. Okay, so now we have understood all the fabrication steps. Of course, I have not discussed packaging part of this. We'll see the packaging part wherever any sensor will require. Okay, so by this I am sure that you have some basic understanding of different types of sensor. If I ask you different classification of sensor, you can easily classify them. You have the basic understanding of the fabrication of the sensor. Okay, so with this I will end up this module 1. Okay, we'll meet in the second module with the different characteristic of sensors. We'll mostly focus on the static characteristic of the sensor because they are very crucial. Thank you.